Good morning, everybody. Okay, do you have any, I'm sorry, do you have any questions to begin with? Okay, so let me share the screen. One second. Okay, let's check something quickly in here. Okay, I'm gonna share the screen. Okay, so there's no questions? Material related homework or whatever form of questions that you have or concerns? Okay, so we are going to continue on with the business of Smith charts. As I told you, it is just like a calculator, for RF design and analysis and measurements. So it makes everything really, really easy. So as you'll see today, excuse me, when you are given the load, you can simply use the Smith chart to determine its reflection coefficient, both magnitude and the phase. We can also determine the admittance if you have impedance. We can solve for any input impedance, of any of these transmission lines. We can solve for the locations of the max and min. Many different things that you can do, on the Smith chart. And now that you have done a lot of mathematics, you are going to definitely appreciate the ease of using the Smith chart. So as I mentioned, earlier, the whole premise behind the Smith chart is we start with the so-called gamma or complex gamma plane. And as I said, is not really anything, like difficult to understand or to see what is going on. It is just a bunch of like millions of dots, of different gammas, depending on what the load is that you put together, and the whole thing becomes like a circle with basically millions of points on it. But the thing is that that you want to notice is that because gamma cannot be bigger than 1, so your gamma plane, it is a circle with a radius of 1. So everywhere you go, you just, the magnitude of, or the radius is going to be 1. So it cannot exceed 1, which is expected. Some special points on this are at this point, when gamma is equal to 1, this is the open circuit, the location of the open circuit. And then this point D is since gamma is -1, then it is going to be the reflection of, I'm sorry, the position of the short circuit. And -1 obviously is written as, the -1 here, we write it as 1 e to the power of j 180 degrees, which is equal to -1. Okay, so that is, excuse me, the location of the short circuit. On the right hand side, C is the location of the open circuit. Okay. Then in between, and then if you just have J, you have one, like your impedance is just 1 times J, then the location is going to be up here. If it is -J, the location is going to be down at -1. So that is why you have a circle of radius 1. And then, as I said, depending on what gamma is, and in here I have just indicated we just looked at 2 gammas, where for this one, the load is, or the gamma actually is based on the load volume. Real part of 0.3, imaginary part of 0.4. So we said we connect 3 real part and then 4 imaginary part plus, and then the intersection of the 2 is going to be the reflection coefficient. Since it is a complex quantity, this arrow is going to be the magnitude of gamma, and then from the horizontal axis, to the one to the right. The angle that it makes, with the horizontal axis to the right is going to be theta r, or the angle of reflection coefficient. In this case, the magnitude is 0.5, and that is 0.3 to the power of 2 plus 0.4 to the power of 2. Square root of those will give you 0.5, and then inverse tan of 0.4 over 0.3 is going to give you 53 degrees. So that is how we go from the Cartesian to polar form, as you already have seen. And again, we have a different load now that results in point B. At point B, again, the real part is -0.5. The imaginary part also is -0.2, and that is what you see in here, which results in a magnitude of, or a complex absolute value of 0.54, and then an angle, again, inverse tan of 0.2 over 0.5 is going to be 202. Now, in here, there's ambiguity in inverse tan that you do. Is everybody familiar with the ambiguity of tan and then how you take care of it? This is not electromagnetics. This is like early mathematics. That tan, is going to have an ambiguity in it. Do you know about it? Does anybody know anything about it?
Tangent will only give between the first and fourth quarter, I believe.
One second. I'm sorry. I have to. One second. I have to raise the volume in here. So. Okay, yeah, I can hear you now. Go ahead.
Doesn't tangent only give between the first and fourth quarter, or the first and second quarter?
Well, the thing is that, as I said, theta r, which is the angle of the gamma reflection coefficient, is equal to inverse tan of the imaginary part, which is -0.2, divided by the real part, which is -0.5. Okay, now if you put this in your calculators, what do you get? So let's put this in our calculators. And I want you to do that, please. Everybody should have at least one calculator, right? So this is tan of 0.2 divided by 0.5 because the negatives get canceled. So inverse tan of, so we are going to do second inverse tan of 0.2 divided by 0.5, and that is equal to 0.38 radians, which is going to be times 180 divided by 3.1416 is going to be 21.8 degrees. Okay, so the calculator, what your calculator is going to give to you is 21.8 degrees. But then on here, you see that they have calculated for the angle to be 202. And this is what the ambiguity of tan means, because when you have a minus in the numerator and one in the denominator, they cancel out. So you are basically calculating the inverse tan of plus 0.2 divided by 0.5. So you lose the information in doing that. That 0.2 is negative on here, and minus 0.5 is negative up there. But by canceling those, I mean, you can put it as minus 0.2 divided by minus 0.5, but still you are going to get 21.8 degrees. Now, how you take care of this ambiguity, which means you go from 21.8 to 202, and 21.8 is wrong, even though your calculator is giving it to you, but the calculator cannot take into account the ambiguity of tan. So accordingly, what happens, yes, you put it in your calculator, you get 21.8 degrees. But then you argue that, 21.8 is in the first quadrant, but minus 0.5 and minus 0.2 over there at point B are in the third. Okay, so how would you go from the first to the third quadrant? You just add 180, add to that the 21.8. So 180 plus 21.8 is 201.8. They have taken it to be 202 degrees. That is what we mean by ambiguity of tangent, because again, you have two negatives, but when you put it in your calculator, the calculator is going to cancel out, the negatives, as is going to give you 21.8 degrees. Did anybody put it in the calculator, just like inverse tan of minus 0.2 divided by minus 0.5?
Yeah.
How much did it show?
Yeah, it was 21.8.
What'd you say? I'm sorry.
Yeah, when I did a minus 0.2 divided by minus 0.5, it was 21.8.
Exactly, because again, the calculator does not understand that, minus 0.5 and minus 0.2 is going to be in the third quadrant. So when you do the homework or in the test, when you see something like this, you have to be aware, and you need to take care of the ambiguity in tan. Okay, now how we and I don't know how many people have seen this, this Smith chart, so as you can see, there's a combo of let me one second. It's a combination of what happened? I want to go into the pointer, and it doesn't give it to me. What happened? Oh, okay, I did it. So if you look closely, you are going to see circles that are just like that. And as you go to the left, they become larger and larger. You see that? The radius becomes larger and larger. So we have a combination of all these circles. And then you see these, right? This one, this one, this one, you can just, and then the same exact thing of the upper half is going to be happening in the lower half. So basically you have, and this is a circle, but because the radius is equal to 1 and gamma cannot exceed 1, you start the circle, but when you reach 1, you have to stop it because beyond 1 is not physical. So the whole thing is that Smith chart is a combination of many, many, many different circles, and some of them are in this form, okay, and some are in the other form that I just showed to you. Now, to see how that comes about, we are not going to spend too much time about it because applications are more important, but still you need to know where the chart is coming from. So basically we start with the gamma is equal to ZL minus ZO over ZL plus ZO, but we divide up both the numerator and denominator by ZO, and we get small case Z of L minus 1 and small case ZL plus 1, where this small case, sorry, I need to know how I can get the, okay. So this Z sub L with the small case Z is called the normalized impedance. And we are totally allowed to do that. I mean, we can take any number and divide any rational number and divide the numerator and denominator by the same value, and it's going to be a lot. So the only thing is that Z sub L, remember the lowercase. And now, because when I write Z like that, I don't know how you are going to translate this. Is it going to be the uppercase, lowercase? If it is the normalized one, which is the lowercase, I put a tilde on just to, to distinguish between the impedance itself and then the normalized one. Okay. So then using this equation, ZL minus 1 over ZL plus 1, we can solve for Z sub L in terms of 1 plus gamma over 1 minus gamma. Remember, I told you the whole Smith chart, all those angles, circles that you just saw, they are the transformation of gamma, values of gamma to on the complex gamma plane to the impedances, which means that we know that the gamma is going to be, as we saw in here, is going to be just a circle with infinite number of points, on it. So if we can take these gammas and translate them to the impedance, then that is the basis of the Smith chart. So basically it is just mapping the gamma into ZL. But that is easy. I mean, here, gamma is equal to this. Solve for Z sub L, 1 plus gamma over 1 minus gamma. But notice that gamma is a complex number in general. So it's going to have a real part, here, the real part and an imaginary part. So so is Z sub L. The load, in general is complex. If it is real, then you just set this imaginary part equal to 0. But in general, for the sake of completeness, we have to write it down as a complex number, and gamma also has to be written down as a complex number, because gamma again has to do with Z sub L, and if that is complex, then gamma is going to be complex. Okay, so first we spell out the load. It is going to be the real part, R sub L plus JXL, and XL could be capacitor or an inductor. If it is inductor, then yes, plus J, whatever the inductance is, and then minus J if the imaginary part is capacitance. Okay, so this is the general form of ZL when you break it down into the real R, and J is the imaginary part. So we go back to equation 2.112. This is the same identical number of the equation number in your textbook. We just replace this by this guy, and then gamma by the real part plus the imaginary part. So this is the sub L normalized is equal to 1 plus real part of gamma plus j imaginary part, and 1 minus real part of gamma minus j imaginary part. Okay, so so now we can separate the real part and imaginary part of the impedance and write it in terms of gamma again. So when I say we map from gamma plane to the impedance plane again, is how you relate or how impedances are going to be related to gamma. So we are trying to take those gamma values and map them in the form of impedances. And that is basically doing this equation. You know, we have gamma plane, we write the impedance in terms of real and imaginary part of gamma. So now if we separate, because this is real part plus imaginary part, if we separate the real part from the imaginary part of this expression here, the real part is going to turn out to be like that. And then the imaginary part is going to turn out to be this. Now, do you know how to separate the real? Because your calculator is not going to do that. And at some point, you have to do it yourself. Do you know how to separate the real part and imaginary part, the rational expression here? How did I arrive at this, R sub L and X sub L? So this is all a complex number. How am I able to take the real part of this and say it is equal to R sub L, and then take the imaginary part of this whole thing and say it is the X sub L? How can you do that? There are no numbers in here, so you would plug in into your calculator. So you need to know how, given a rational complex, expression, how you can separate the real part from the imaginary part. Do you know how to do that?
Wouldn't you multiply by the complex conjugate?
Exactly. So you are going to multiply both the numerator and the denominator by the complex conjugate of the denominator. When you do that, any complex number times its complex conjugate is going to be its magnitude to the power of 2. So the magnitude is 1 minus gamma r to the power of 2 plus gamma I to the power of 2 square root of that. But it is the magnitude to the power of 2, so therefore it is going to be 1 minus gamma real to the power of 2 plus gamma imaginary to the power of 2. That is going to be your denominator, so you divide this by this guy and you get the real part, and then you divide j by after you multiply by the complex conjugate of the denominator, obviously. Then you can separate this into the real and imaginary part. Once you do that, this is going to be the real part of the impedance, and this is going to be the imaginary part of the impedance. The important thing is, again, remember, we wanted to start from gammas on the gamma plane and transform to the impedance. And that is exactly what these two equations are going to do for us. So for any given gamma, so let's say for the same gammas here, 0.3 plus 0.4. So this is 0.3 and this is 0.4, real part, imaginary part. So you plug this in, the same thing in here, and you get the real part of the impedance. So that is how we can use gamma to come up with real part of the impedance. And then the same thing with how we can use, again, gamma, the real part, the imaginary part, to related to the imaginary part of the impedance. Now, excuse me. If you manipulate this equation here, okay, because like this, it doesn't show how the gamma, or the real part of the impedance is related to, you see how it is, 1 minus the real part, blah, 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 all of those, but it doesn't really give you like a shape, so like R sub L is related to gamma in what form, I do these, okay, given the gammas, I do these and I get the corresponding, real part, and the same thing with the imaginary part. But to make it more obvious and get to what Smith chart is, we can manipulate this equation right there. And then if you manipulate, you can arrive at this equation down here. So basically this can be written as this, okay, along with R sub L. So all it is, you multiply R sub L by the denominator, so just cross multiplication. This one also by the denominator, which is 1. So you have this times the denominator is equal to this up here. You play with this a little bit and try to write it in this form. Now, what is this form? X squared, x minus x0 to the power of 2 plus y minus y0 to the power of 2 is equal to r to the power of 2. So the equation is for what? So what is the equation?
A circle.
Of a circle that has a center at x0 comma y0 and a radius of a. So this is a circle, okay, of the radius of the center of this. This is your x0, okay, and plus y, and the y component of the center in here is 0 because it is just, gamma I to the power of 2 y squared. So there's no y0 is equal to the radius to the power of 2. The radius is going to be 1 over 1 plus the real part of gamma. So what does this mean? This means that for any given value of gamma, the real part and imaginary part this is the load, the real part and imaginary part of gamma, we can actually take those numbers, as you see in here, when we compared it with the equation of a circle, and relate it to the impedance in terms of circles that have a center on the x-axis, or rather this axis here, okay, and y is going to be equal to 0. Y0 is equal to 0, so the center is going to be all the way here. And so there are going to be tons of these circles because, again, if you look at this, if you look at this equation, the equation of a circle, the center, did I write it in here? Let me write it for sake of completeness. I don't know how to get this thing back. So it has a center at, one second. I don't know why it just, let me just exit and come back to that should fix it. Let me maximize this. Okay, so as I said, the center is going to be at RL over 1 plus RL, the real part of the normalized impedance, comma 0, and the radius is going to be 1 over 1 plus R sub L. Okay, so that is the equation of a circle, equation 2.116, with a center of this and a radius of that. Now, if you notice, the center for this equation, 2.116 here, is going to be all the centers are going to be along the x-axis because their y component is equal to 0. Okay, and then their radius is going to be 1 plus 1 plus R sub L. If you have a short circuit, I'm sorry, let me. Okay, if you have a short circuit, then R sub L is equal to I mean, if the load is short or open circuit, you know, you are going to, for example, if it is, I mean, if the load is short circuit, then the impedance is equal to 0. Therefore, the real part is going to be 1/1, which is equal to 1. And that is exactly what I told you, the location of the short circuitness and then also the open circuit. But the point is that for any given value of gamma, okay, you can, it is a circle for the impedance, the real part of the impedance, again, that have centers at this and a radius of that one. Now the center again is going to be on the x-axis only. There's no y up or down, and that is exactly what you see in here. So you see these are the circles. So this is for any for some, you know, given some gamma, we are going to get this circle, because again there is infinite gamma, but you know that gamma is related to the impedance in the form of a circle because of this one equation here. Okay, so if you take this and say, okay, we start like this, we say, what about if gamma is equal to 0.1? Then you put real part equal to 0.1, imaginary part equal to 0 because it's just 0.1, and then you can go ahead and draw the circle for a gamma whose real part is 1 and imaginary part is equal to 0. If you plug in that and then plot, so here, for example, this is a circle, okay, that we had. So, or this one, this is the initial form, this is the circle that we have. Let's say gamma is going to be, its real part is 0.33 and imaginary part is equal to 0. So that is a point of, if you put the real part 0.33 and the imaginary part equal to 0 in here. Okay, so there's going to be 1 plus, I'm sorry, minus 0.33 to the power of 2, blah, blah, blah. Just put these real and imaginary part numbers in there, and you are going to get a point on here. Okay, it is a circle when you turn it to R. Then you go ahead and put the real part equal to 0.5, the imaginary part 0.29. Again, it is going to be on the circle that is a circle of 2, for example. So, and you keep doing that. So the real part is equal to 0.1, imaginary part is equal to 0.3, minus 0.1, minus 0.5, blah, blah, so on and so forth. And there is millions of combinations of this that gives you a R sub L that is equal to 2. So for example, this one, can somebody do this quickly, please? We have this gamma, okay? We want to know the corresponding impedance, the real part and the imaginary part. We know the real part is a circle and is related to gamma by this equation. So I say pick the real part, done to be 0.33, and the imaginary part, that one equal to 0. Do this, see what R sub L is going to be. Can you do it quickly in your calculator, please? Right now.
I'll get 1.9985. So
Okay,
around 2.
2.
Yeah.
Right, so the real part of this combination is equal to 2. And this one is going to be where? This is going to be 0. Yeah, this is the real part. And the imaginary part is equal to 0. So you are looking at this point right there. Okay. Now put 0.5 for the gamma R, 0.25 for gamma I. What do you get in this equation again? What do you get? Are you guys doing it on your calculators? Can you do this? Put
Yeah,
this
so
equal to
I got 1.52.
no, that you didn't do it correctly. Let's do it. I'm going to do it. Okay. So the numerator is going to be 1 minus 0.5 to the power of 2, and then minus 0.29 to the power of 2. Okay. So this is your numerator. Delete. Okay, and we're going to take this and divide by 1 minus, let me do the denominator first. So it is going to be 1 minus, the real part is 0.5, is 0.5 to the power of 2 is 0.25, plus the imaginary part is 0.29, 0.29 to the power of 2 is going to be 0.3341. Now I'm going to do the numerator. So numerator is going to be 1 minus 0.5 to the power of 2, okay, minus 0.29 to the power of 2, okay, and that is going to be 0.6659. If I take 0.6659 and divide by the denominator, which is 0.3341, I'm going to get 1.99 as the real part. So therefore, this point also corresponds to the gamma, the circle that is equal. The real part is equal to 2, or the real circle that is equal to 2. Now you can just keep going down. Okay, another gamma, real part, imagine. So there is millions of these combinations that all will give you a real part of 2. When you put all these, millions of combinations that will give you R sub L, then you are going to get a circle. Okay, you connect all these points together, the millions, you get a circle that is called the real part, the real circle. We don't say real part, the real circle that is equal to 2. Okay, then you can choose an entirely different sets of numbers. So let's say you want to have the real circle of equal to 0.5. Okay, so you put 0.5 in here, and then, or rather, there is going to be a combo of gamma, the real and imaginary, that if you put in this equation is going to give you 0.5. Just like the one that we did for 2, now we do the same thing for 0.5. There's going to be millions of gammas, real and imaginary part, just like these, that if you map it, over here, basically you put, those numbers that you get for R sub L, then they are going to form a circle that is going to be, when you connect all the points, different gammas, millions of gammas, they all end up to be the real circle of 0.5. Okay, now we can do the same identical thing with the imaginary components. So you remember R sub L is the real part of the impedance, and X sub L is the imaginary part of the impedance. Now, X sub L, the imaginary part of the impedance, is related to gamma like this. Now, since you saw the real circles, if you put an X of L is equal to this, how many gammas are there that if you put the imaginary part and the real part of those gammas, they all end up to give you, let's say, 2, this X of L of 2, just like the real part. How many different gammas can you put in here to give you X of L of 2, you think? Is there just one gamma that will, if you put the real and imaginary, gives you a 2? Is there going to be 10? Is there going to be 100? How many gammas would you say are there that if you put the real and imaginary part of those gammas, it will give you an X of L that is equal to 2? Nobody knows. Just like this. In this one, we had the real part equal to this, and we said there are if we said this equal to 2, then we said there are infinite choices that if you put them in here, you get 2. Another one put here, you get 2. Another one put here, you get 2. And when you connect all those to each other, then you get this circle. Okay. Now we have the same kind of equation, but a bit different, but it is the imaginary part of the load, again, in terms of gammas. So if the real part gives you millions of these gammas, that is equal to 2, then if I put the imaginary part also equal to 2, there ought to be millions or infinite number of gammas that if you plug in here, just like the real part, is going to give you 2. But when you connect all those points that you put in here to get 2, then you are going to get something like this. Okay, this is a circle that you can draw and go beyond, and then come back, right? But anything above, because this is 1, minus 1, plus 1, I'm sorry, j, minus j, remember the gamma plane? J, minus j, 1, minus 1. Okay, open circuit, short circuit, j, and minus j. So as you draw the circle, and it goes beyond 1, then it is going to be non-physical. There's not such a thing that its gamma would be bigger than 1. The other thing that we want to notice is that the center now is always a 1 in x and 1 over x of L in y. Now look at all these circles. If you draw these circles, their centers always is going to be at 1 over here, and then up here or down here, depending on 1 over x of L, whatever that number is going to be the y part of it. So the center is going to be 1 and something. Do you see? This is the center for this one. 1 and, I'm sorry, 1 and something will give you the center of this one, and the same thing. So the centers of these circles, all of them are going to be at the real part equal to 1, or the x0 is equal to 1, and y0 is equal to this. Okay. Excuse me. That is as far as the center is concerned. The radius is going to be this 1 over x of L. So for this one, for example, the radius is going to be, the center is going to be here. From here to here is the radius. This is the radius of this circle. So depending on how much the imaginary part is, the radius could be smaller, or for the bigger ones, it is going to be bigger. Okay, but notice that the center, depending on x of L, if it is positive, then the centers are going to end up to be up here. Okay, if x of L is negative, then the centers end up to be in the lower side of the Smith chart. So these ones are for the real part of the impedance, these round ones, okay? And then these ones that are kind of diverging out of the circle are for the imaginary part. So imaginary part could be inductive, in which case you are using these, or it could be capacitive, in which case you use these circles. Okay, so now to begin with, I have it on the next page, but let me write it out here as we are looking at this together. So let's say we have a Z L that is equal to 50 plus J 100, and ZO is equal to 50 ohms. This is ohms. Okay, we want to take this and map it on the Smith chart, which is now the combination of the blue and red circles. Reds are for the real part, blue are for the imaginary part. So the first thing that you do, if you remember, we said we normalize. So this is going to be equal to 50 divided by 50 is 1, and 100 divided by 50 is 2. So this Z sub L now is going to be a circle that has a real part of 1 and with another circle that has an imaginary part of 2. So if we can find the intersection of circle real of 1 and imaginary of 2, that would be the location of the slope, the normalized value on the Smith chart. So all we need to do is the real circle, just this is the 1, it says equals 1. The imaginary is equal to 2. It is this circle right there is equal to 2. So we need to find the intersection of this with 2. And if you go around this is circle 1, all of them, right? For many infinite number of gammas. So the real part is equal to 1, which is that point, and the imaginary part is equal to 2. So your impedance, the location of the impedance of the Smith chart is going to be exactly at that point that the yellow that I put on here. So you can now put all the the real parts of point. You can say even the real part of 0.1, then 0.2, 0.3, 0.5, all the way to 1, because again, remember, it cannot exceed 1. And then if you do that, you are going to end up with these this beast that is a combination of all. If you notice and you look closely, you see all these are the real circles, and these are the imaginary ones. Do you see? And I put as many as we could, because you have to be able to distinguish. If you put all of them, then it becomes like a black background. There's no lines, so they are either there or or you have there are close ones that you can approximate. So again, let's do now another one, Z sub L. So we have a Z sub L that is equal, let me choose a better color. We have a Z sub L that is equal to 100 minus J 50 ohms. And the transmission line characteristic impedance is equal to 50 ohms. Usually it is 50 or 75. So again, the first step is you normalize the impedance, and if you do that, you are going to get 100 divided by 50 is 2, minus 50 divided by 50 is 1. So minus J 1. So Z sub L on the Smith chart is going to be the real circle of 2 and imaginary circle of minus 1. So the real circle of 2, do you see the 2 in here? Do you see it? Do you see the 2? So this is 3, this is 4, this is 2, right? So we are going to be on this circle, okay? Somewhere on this circle. But the point on the circle that relates to this particular load is the intersection of 2 and minus 1. So 2 is in red, minus 1 is in green. So we look for it. See, the real circles, it tells you the values on the axis. So all you need to do is to look at here. This is circle 3, and this is circle 0.3. So the corresponding one, okay? Imaginary circles, it says it at the end, at the perimeter of the Smith chart, okay? So if you are looking for an imaginary part of 1, then we look on the perimeter here, and you see this is 1. I'm sorry, 0.3, 2, let me see, 1 over here. Do you see it? 1. And then 0.9, 0.8 here, 1.2. So you go, this way. The circles are getting bigger. You go that way to the left, the circles are getting smaller, the volumes. So you need the intersection of 2, which is the red one, and j minus 1, which is going to be, you just follow this all the way to here, and the intersection of the red and the green is going to be +2 and -1 is going to be the location of the load, the normalized one on the Smith chart. Okay. I think I asked you to have Smith charts handy. If you don't, please make sure, because the next few lectures are going to be on the application of the Smith chart. So we are going to be using it a lot. So do you have a Smith chart available? Or it could be if it is on your laptop or iPad, those kind of things, you can use it that way as well. But do you have access to Smith chart?
I got one printed out.
I'm sorry?
Yeah, I've got one.
Okay, so if you don't have one, please get one right now, because you need to do the work. Okay. So I'm going to write a load impedance and ask you to locate it on the Smith chart. So Z sub L is going to be equal to, this is the most important part of the application of Smith charts, how to put the loads on the chart. Once you do that, and if you do it, correctly, then everything else is going to be correct. So Z sub L is 150 plus J 75 ohms. And ZO is equal to 75 ohms. Can you locate this load of 150 plus J75 when ZO is equal to 75 ohms? Can you do that, please? Does anybody, let me put it this way, does anybody have trouble given impedance to put it on the Smith chart? So everybody in here, because I'm gonna assign you homeworks, and then there's gonna be quizzes, exams, all sort of things. And I don't want you to go and try to learn it from the book. Otherwise, what am I doing in here? I'm here to help you to learn. So you need to make sure that you know how to do it. If I have to do 10 more, so you would learn how to do it, I'm more than willing to do so. Again, I ask one final time, everybody in the class, you can locate, given the load and the ZO, you can locate the position of the load on the chart. Is that true? Or you have?
Yeah.
I was able to follow.
Anybody who is not?
Yeah, I'm fine with that. I just had another question. Can you go over the
Sure.
equation on how you're getting the little ZL again?
The equation, which one?
On just how you're getting little ZL.
Oh, ZL, yeah. Here. You start from ZL minus ZO over ZL plus ZO, and you divide by ZO, you normalize by ZO, then you get ZL over ZO minus 1, ZL over ZO plus 1. Then the ZL over ZO is the lower case, which is the normalized impedance, and then -1 and +1. So that starts from gamma is equal to this one we know for a long time, ZL minus ZO over ZL plus ZO. Now, if you divide both the numerator and denominator by ZO, then you get ZL over ZO minus 1, the whole thing over ZL over ZO plus 1. And this is the normalized, so we can now write it in terms of the normalized value of Z sub L. Do you see that?
Yeah, I'm good now.
Okay. So was everybody able to put this on the chart? Again, from next time, I need you to have a few, you can print it out. If you Google, there's hundreds of millions of, but the only thing is that when you do the Smith chart, you want to print this one, because there are some that only has the circles, but it doesn't have this at the bottom. So a lot of them, they have this, the ones that you find on Google, but they don't have this measuring tape, sort of. So it has to be this whole thing. So I want you to please, from Thursday on, bring a few of these videos so you can actually do it on your desk as you are sitting and listening to what I'm saying. If you don't have those ready right now, see if you can work on a digital one, the same way that I'm going to work on this one on my what is it, the tablet. Okay, so now the first thing that I want to teach you is how to use the Smith chart to not only locate the load, but find out the reflection coefficient, both the magnitude and the phase of the reflection coefficient. So both gamma, so that is what I'm going to do in here, given, and I'm going to do the example that is on here. So we have a load that is 60 plus J43 and a Z of 50, 60 plus J43. So ZL is 60 plus J43. I intentionally wrote it as, these are going to be fractional. And then ZO is equal to 50. Okay. We want to, for the given ZL, we want to determine gamma, which is the reflection coefficient. Now remember, gamma has a magnitude and a phase, theta r. So the Smith chart, without doing any numbering, any calculations, is going to immediately give you the magnitude of the reflection coefficient and its angle. Okay, but the first thing is you need to know where the normalized value of Z sub L is going to be. And in order to do that, so number one, the normalized. So ZL normalized is equal to 60 divided by 50 plus J 43 divided by 50, which is going to be 60 divided by 50 is 1.2 plus J 43 divided by 50 is 0.86. So this is the normalized value of the load, and this is the one that I'm going to put on the Smith chart. Okay, so then I go over here on the chart and to determine the intersection of 1.2 and 0.86. So this is 1.2. Do you see it? Because of the size of, the PowerPoint thing, I cannot make it bigger, but this, once again. So this is circle 1, this is 1.2, this is 1.4, 1.6. Do you see that? 2, and so on and so forth. So I need the real part to be 1.2. So it should be on the circle. Okay, 1.2. But the imaginary part has to be 0.86. Okay, so this is 0.1. I'm sorry, this is 1. This is 0.9. 0.8. So if it is 1 and this is 0.9, then this is going to be what is it? 1 and 1.95, right? And then 0.8 and 0.9, this is 0.85. You see that? So we go a little bit towards 0.9 because it is not 0.85, it is 0.86. So, let me see, 1 point, it's difficult to see, but 0.9, 0.8. So this over here, you just continue with this, okay, till you reach circle of 2, okay? And this is going to be the circle of, which one is it? 2? Yeah, 2. So it's going to be this. Let me draw it. So this is 2. So I'm going to draw it up here. It's a circle 2. And then I'm going to draw the 0.86. Again, this is 0.8. This is 0.9. This is 0.85. Somewhere here. We just continue with this. And you finally find the intersection between the two, and that is the location of the load. Okay? Does everybody see how I did this? Again, this is the concept of locating the load on the Smith chart. Is everybody good with that?
Yeah, it looks good.
Yeah, that makes sense.
So now, what I want you to do, if you have the Smith chart, available to you, I want you to grab a piece of paper. So that is going to be your right hand, the piece of paper, just scratch paper. It doesn't have to be any special or whatever. Just take a piece of paper. The first thing you want to note is the center of the Smith chart, and this is the center. Okay, it is 1 minus 1 and j and minus j apart. So that is the center. Then what I want you to do is to put the piece of paper along with the point that is green. So on your paper, just put a mark, at where the center is. So I put a mark in here. And then go ahead and put a mark at the end where the red is, where the location of the load is. So now I have on the piece of paper, I have, one second. On the piece of paper, I have a mark that is here, and another one that is going to be there. So the piece of paper gives me this line. Okay, so I want you to connect now using the piece of paper. The first thing is you make 2 marks on the piece of paper. One is over here and one is there. But before moving the piece of paper, go ahead and draw a straight line from the center, passing through the point that we are looking at, and then going all the way to the perimeter of the Smith chart. Okay. So we are going to be, after making the 2 marks, we are going to do something like, here, go to the location of the load and continue on to the end of Smith chart. Okay. Now, in order to measure the magnitude of the Smith chart, let me see if I can actually zoom in a little bit. don't know if it is gonna do it, but yeah, it doesn't do it. So I don't know in the PowerPoint when we are in the presentation mode. Let me 1 second if I can. Oh, this is really small. Let's do it here. Let me see if I can. No, unfortunately, it doesn't work. On the PowerPoint, I'm trying to. Why did it go to? Apparently, it does. So, all right. Let me. Does it for the other pages, but not for this one? It's interesting. Yeah. Yeah, I don't know why it is not. Oh, okay. So, so now you can see this, the circle of 2. Okay, I don't have the pointer, but this is circle 2, and then this is a circle. Again, this is 0.8. This is point. Yeah, this we have to. That is why I'm saying that you have to have a good look at it, because this is 0.9. This one, and this one is. I'm sorry. No, this one is 0.9. So this is 1. Then this is 0.8. So the middle of this and that, which is this one, is 0.9. Okay, but it is not 0.9, it is 0.86. So it is a little bit to the, I mean, this way. Okay. Oh, escape. All right. Now you have the you have drawn the line all the way, going through the perimeter. If you did that, then oh my God, didn't know that just the whole thing is gonna okay. So let's see if I can move the. Don't know why it just moves the. Okay, something like that. All right. I don't want to waste time in just, come on, 10 things. Okay, we'll just, all right, good. Now, if you, I don't know how to move this whole thing together, but let's, let me see if I do the, would keep it as, no, it doesn't. Anyways, there's limitations, when you do the remote stuff. So, okay, so we extended it all the way to here. Now, I want you to try to read this here. It says angle of reflection coefficient. Do you see that? Can you read this? Angle of reflection coefficient. Can you read that?
Yeah, I see it.
So, okay, so do you see the numbers here that are related to angle of reflection coefficient? So these are the angles. So for example, this is, let me see. It hurts. So this is 20, right? Degrees. This is 30. So if this is 30, this is 20 degrees. So this would be about, I would say, 28 degrees. So theta R theta r is going to be about 28 degrees. Okay, note that again, I'm working on a very small, relative picture, and making mistake on a graphical thing that is so small, is going to be really hard to do. Okay, so we just determined the angle of the reflection coefficient, which is about 28 degrees. Okay, and you read it again where it says the angle of reflection coefficient. Now we go back to the scratch paper. You remember you had 2 marks on it, but one at the center, one at the intersection, the location of the load. Now look down here, you see the center. One second. You see the center, right? It says center. Now continue on with this, and over here, what do we read? Reflection coefficient, right? You see that? Reflection coefficient. So you follow that, it comes to this line that is a center. Now what you need to do is, you remember you have 2 marks, okay, on your scratch paper. So what I want you to do now is, and you have to do now, is to go ahead and use one of the marks and mark it at the center. Okay, so I do it that way. And then you have the second mark to the left, and wherever that one is, you just draw a line there. So this is 0.5, this is 0.4. I would say about 0.45, right? Something like that. So gamma is going to be about 0.45 e to the power of j, 28 degrees. Okay, I did this on my own Smith chart at home, rather, and let's see what I got. I got, okay, ZL, we did it. Gamma is equal to 0.37, 57 degrees. Yeah, I don't know why, but the angle we are off. Again, I'm looking at the very small number, but the real part is 0.37. So let's see, 0.45 again, because this is not really visible, as much as the one that if you work on it at home, is going to be much better. But do you see how the procedure is done? You first locate the load in every, you first normalize. Then you are going to locate ZL, which is the normalized impedance. Then you are going to draw a line from the center to location of ZL and beyond, which goes to perimeter. Okay. Then you use a piece of paper, make 2 marks, one at the center and another one at the location of Z sub L. Then you go to the bottom side, tape measure, and measure magnitude of gamma. And when you go to the beyond and perimeter, you have to, give me one second, you have to read theta r from where it says the angle of reflection coefficient. Okay. Now you have the angle up here, and then you have the magnitude down here. You have the gamma, or the reflection coefficient of this particular case. Is everybody okay with doing something like that? something like this. Given ZL and ZO, can you normalize, locate it on the chart, and then draw the straight line, blah, 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 all that I have said and put in here. Can everybody do that?
Yeah, it looks pretty good.
Okay. All right. So again, I forgot and not forgot. I mean, when I get into these things, you know, my head goes like, gets focused on one thing only. So we just have to do the quiz on Thursday and see how things go from that point on. But definitely Thursday, no matter what, I'm going to put a timer and on my phone, and then we are going to have the quiz. If you don't have any questions, I'm going to post this one plus the obviously the video lecture and I mean the video of this lecture, and probably assign homework. I'll see either today or Thursday. Okay. All right. If you don't have any questions, then I'll see everybody on Thursday.
Have a good afternoon.
Thank you. You too.